I've had a few requests to cover interrupts on Arduino. Before we do that, we need to talk about registers. So, what is a register? To answer that, we have to look at the datasheet for our microcontroller, which, on the Arduino Uno R3, is the microchip AVR ATmega 328P. The datasheet is a 660-page monstrosity that tells you everything you need to know about the 328P and its siblings. If we look at the CPU core overview, we find a block diagram showing how the main processor is configured. The ALU, the arithmetic logic unit, is responsible for performing calculations like addition, subtraction, bitwise logical operations, and so on. Data can come from or be stored to 32 general-purpose registers, each holding 8 bits, or 1 byte. Other registers exist, like the instruction register, or within I/O modules to assist with pin control. Think of the processor like a kitchen. The ALU is the chef whose job is to follow instructions and prepare meals, the person that's responsible for executing all the actions. The chef is following a recipe, which is like the program you wrote, a series of instructions for the ALU. The pots, pans, and various bowls for prepping food are your registers. They're simply containers for holding food. In the processor, they're storage vessels for data. The general-purpose registers are used to hold data for calculations. The kitchen analogy breaks down when we start talking about special function registers. These registers have special hardware connected to them in the microcontroller die. Let's pretend that these tiny bins represent bits in a special function register. In our 328P, each register has 8 bits, and we are able to read and write to many, but not all, of these registers directly from code. For example, I can set a bit to 1, which I'll represent as a closed lid. The open lids represent the binary value 0. The register has the binary value 00100110. To calculate the decimal value from this binary number, we start from the rightmost bit and assign it the value 1. The next bit to the left has the value 2, then 4, then 8, 16, 32, 64, and 128. Notice that the value doubles each bit we go up. For the bits that are set to 1, we add up their assigned decimal values. For example, this would be 2 plus 4 plus 32, which is 38. If we were to write this value to a certain special function register in the microcontroller, it might cause corresponding hardware pins to go from 0 volts to 5 volts. In fact, we're going to do just that. Special function registers are used to control pins, set up interrupts, send and receive serial data, and so on. Note that registers are unique to each architecture. That means if you're developing on a 328P and you move to an ESP32, you'll need to learn a whole new set of register names. The 328P has 3 different types of memory. The first is program memory. This is where your code lives. When you write code for the 328P, it is compiled into machine code and stored here. It's the set of instructions, or recipe, for your processor to follow. Next is SRAM, or static random access memory. The interesting part is that our general-purpose registers, as well as the special function registers, at least the ones we have read or write access to, live in the first 256 spaces of SRAM on the 328P. So, to write to a special function register, we need to first find its address in SRAM, and then we specify what value we want to write to it in our program. The rest of the SRAM is used to hold values for things like variables when you define them in your code. Note that when you power down or reset your microcontroller, the SRAM is cleared, so you lose all your data here. Finally, there's electrically erasable programmable read-only memory, or Eeprom. It's often not considered part of the memory of the processor since it's usually on a separate bus. It also has much slower read and write times, but it's useful for storing data that needs to be saved between resets or when power is lost. If we look at the I/O ports overview section, we can see what a digital input-output pin looks like in a general sense. Note that on the 328P, every I/O pin can be configured to act as a digital input or a digital output, although some pins can adopt other functions like serial transmit, hardware interrupt, or analog to digital converter. Go up to the pin configurations section and take a look at the DIP package, which is the same one found on the Arduino Uno. You'll see that I/O pins are given a label P for port, a letter like B, C, or D, and a pin number. For example, we may want to toggle an LED on pin PD5, which stands for port D, pin 5. To use a pin as digital input or output, we need to be concerned with 3 registers: port, DDR, and pin. Let's navigate to the I/O ports register description section to take a more in-depth look. First, we need to set the DDR, the data direction register for our port D in this case. By writing a 1 to a bit in the DDR, we're telling the microcontroller that we want the corresponding pin to be an output. We want to be able to control the voltage on that pin with our code. If we leave the bit a 0, then we want the pin to be an input, which means we can read whether the voltage is high, around 5 volts for our Arduino, or low, around 0 volts. Next, we have the port register, not to be confused with the hardware port, which is a collection of pins. Note the all capital letters for the register name. If a pin is configured to be an output from the data direction register, then writing a 0 to the corresponding bit in the port register will cause the pin's voltage to be 0 volts. And writing a 1 to the corresponding bit will cause the pin's voltage to go high, 5 volts in the case of our Arduino. If, however, the pin is configured to be an input, then writing a 1 to the same bit in the port register will enable the pull-up resistor on that pin. Leaving it 0 for an input pin will disconnect the pull-up resistor. As you can see, the port register performs 2 duties depending on if the pin is an input or output. Finally, the pin register should generally be treated as read-only, and its purpose is to give you the input values on the pins of that port. We'll look at an example of how to do this in a minute, but first let's see how these registers are organized in memory. If we navigate to the register summary section of the datasheet, we see the registers listed with their addresses in SRAM. Note that they're in reverse order. Special function registers can have functions other than controlling pins. For example, TCCR0A is used to control timer 0, which is useful for things like setting interrupts and creating pulse width modulation signals. Some bits are unused or reserved as noted by a dash. And likewise, a whole register may be marked as reserved. These usually have special functions internal to the processor and generally should not be written to. Let's start with a very simple Arduino example. Whenever a button is pushed, an LED lights up. It's trivial, but it serves as a great way to see how to use registers to control hardware. Starting with an LED and button on a breadboard, put a 330 ohm resistor in series with the LED's anode. Connect a wire from the resistor to pin 5 on the Arduino. Connect another wire from the LED's cathode to one of the button's pins, as these pins will share a common ground connection. Then connect those pins to ground on the Arduino. Finally, run a wire from the button's other pin to pin 2 on the Arduino. We've defined our button and LED pins to be 2 and 5. We've set the button pin to be an input with the pull-up resistor enabled and the LED pin to be an output pin. In loop, we read the state of the button pin, which gives us a 0 if the button is pressed and a 1 if the button is not pressed. If the button is pressed, turn the LED on, otherwise turn it off. The Arduino framework gives us a layer of abstraction. Functions like pin mode and digital read are reading and writing values to the necessary registers for our 328P. Let's upload this code. Notice that this Arduino code takes 902 bytes of program space. This will be important later. Just to test, as we press the button, the LED lights up. Everything seems to be working. What we want to do now is rewrite our program so that we have the same functionality, but we're directly manipulating registers rather than relying on Arduino code. We need to look at the Uno R3 schematic and find the 328P controller. Here, we see that our button is attached to Arduino pin 2, which is PD2, port D pin 2, on the microcontroller. Likewise, Arduino pin 5, which is attached to our LED, is actually PD5. This means we need to manipulate the port D registers to read and write to these pins. Let's say that we have our 3 registers that control port D on the microcontroller. First, we'll set the DDRD register to binary 0010-0000, which tells the microcontroller that we want to use pin 5 on port D as an output for our LED, and leave the rest of the pins as input. Then, we want to write 0000-0100 to the port D register. This will enable the internal pull-up resistor on pin 2, as that pin was configured as an input. Let's make these changes in our code. Remove our pin mode functions and replace them with DDRD equals capital B 0010-0000 semicolon. Note that starting a number with capital B indicates that we're using binary. So binary 0010-0000 is really 32 in decimal. You could replace this number with just 32 and it would mean the same thing. It looks like we're setting a variable named DDRD. In reality, we're calling a predefined macro for the 328P that assigns the value 32 to the register at the DDRD address. If we dig into the Arduino source code, we find a file named iom328p.h, which defines all of our registers for the ATmega 328P. In it, we see that DDRD is defined as a macro used to manipulate special function registers and given the address hex 0A. If we look at the register summary section in the datasheet again, we can confirm that SRAM address hex 0A is indeed the data direction register for port D. Back in our code, we want to add port D equals binary 0000-0100. This enables the pull-up resistor for pin 2. Note that it also causes pin 5 to be set to 0 volts, as we've already told pin 5 to be output in the previous step. Upload your code to the Arduino. Press the button, and we see that our circuit is behaving the exact same way as before. Now, let's try replacing the digital write functions with direct register writes. In the first one, we want to turn the LED on. So replace it with port D equals binary 0010-0000. And we want to turn off the LED in the second one. So replace it with port D equals binary 0000-0000. Upload the code. When I push the button, the LED comes on, but wait, it doesn't turn off. What's going on here? Remember how setting or clearing a bit in the port D register can enable or disable the pull-up resistor if that pin was set to an input? Well, it looks like we're disabling the pull-up resistor for pin 2 when we're trying to turn the LED on and off. Oops. We could change that bit to a 1 in both writes to port D, but this is a good time to talk about setting and clearing individual bits in a register. Other parts of your code may try to set or clear bits in the register, and we want to leave those alone to just make the single bit change we need. So, how do we do that? First, we need to use the left shift operator. This shifts all the bits to the left by the number of positions specified. For example, the number 50 is 00110010 in binary. If we wrote 50 less than 2, it would shift all bits to the left by 2 positions, resulting in 11001000, which is 200. Note that zeros are appended on the right side during the shifting operation. So, to set bit 5, we need to left shift the number 1 over by the number of times equal to the bit's position, 5 in this case. This gives us binary 0010-0000. We then want to read the current value of the port D register, which will likely be something like 0000-0100, as pin 2 is configured for a pull-up. We want to use the bitwise OR operator to perform the OR operation between each of the corresponding bits. 0 or 0 is 0, 0 or 0 is 0, 1 or 0 is 1, and so on. By doing this, we keep all the same bit values that were in port D except for bit 5, which we've changed to 1. We then write this value back to the port D register. In our code where we want to turn on the LED, we change it to port D equals, open parentheses, 1 left shift LED pin, close parentheses, vertical bar for the OR operation, port D semicolon. This shifts 1 to the left by 5 bits, as LED pin is equal to 5, performs a bitwise OR operation with the value currently in the port D register, and writes that result back to port D. The method of setting a bit doesn't quite work for clearing a bit, meaning we want that bit to be 0. To do that, we start again by shifting the number 1 over by the number of times equal to the bit's position, which we'll want to be 5. We then perform a bitwise NOT operation on this result to invert all the bits. 1s become 0s and 0s become 1s. So, in our example, we have 1101, 1111. We then want to perform a bitwise AND operation on this number with the current value in port D. This is likely to be 0010, 0100, as the LED on pin 5 will probably be on and pin 2 still has the pull-up set. Move down the bits again and perform the AND operation. 1 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0. Only bit 2 is kept set in this instance, as 1 and 1 is 1. Notice again that the bit values in port D are kept the same except for pin 5, which we've successfully cleared. In code, this looks like port D equals tilde for the NOT operation, open parentheses, 1 left shift, LED pin, close parentheses, ampersand port D semicolon. This shifts the number 1 over to the left 5 spaces, performs a bitwise NOT operation on that result, and then performs a bitwise AND on that with the value in port D. Ultimately, this clears bit 5 and writes that value back to port D. The last piece we need to consider is the digital read function. Remember that we want to read the value of the pin D register, but we need it so that we get a 0 or 1 for the state of that pin. If we were just to read pin D, we'd get the state of all the pins on port D. So, how do we isolate just pin 2? We first want to left shift the number 1 again by the number of times equal to the bit's position, 2 in the case of our button. We then read the value of the pin D register, which I'll write as a series of X's, as we don't know what state the pins will be in. An X can either be high or low, 1 or 0, we don't know. We use the bitwise AND operation on these values, which is known as masking. Here, we're defining which bit or bits we want to keep, and the only bit we care about is bit 2. When we perform the bitwise AND, the result is 0 for each bit in the first number that is 0. It doesn't matter if the X is 0 or 1, 0 and 0 is 0, as well as 0 and 1 is also 0. The only bit that stays the same is bit 2, as 1 and 0 is 0, and 1 and 1 is 1. So, whatever value was in that bit in pin D is kept. If this X happens to be a 1, the value would then be binary 0000, 0100, which is 4. We want the result to be 1 if that bit is set, so we right shift this result by 2, the same number we shifted by before. Now, if bit 2 of pin D is high, we get 1 as a result, or if bit 2 is low, we get 0. In our code, we replace the digital read line with int btn equals open parentheses pin D ampersand open parentheses 1 left shift button pin close parentheses right shift button pin semicolon. This will set the btn variable to 1 if pin 2 is high or to 0 if pin 2 is low. Upload this program. We see that the circuit is back to working again. To make life a little easier, the Arduino library also has the _BV macro, which is defined for the AVR family of microcontrollers, and our 328P is in that family. The BV macro just makes the 1 left shift by bit number operation a little easier to read and faster to execute. We can replace our left shift operations in our code with _BV bit number. It's slightly easier to read, but it's also important to understand the BV macro, as you'll often see it in C code examples for AVR. We can upload the code to see that it works exactly the same. But here's the interesting part. Remember how our Arduino code was 902 bytes in size? Our newly optimized program now compiles to just 462 bytes. We nearly halved the size of our program by manually reading and writing to registers. If you're making a product and you need your code to be as small and fast as possible, learning to deal directly with registers can be very helpful and get rid of the extra code overhead that Arduino introduces. However, if you're making a project or a prototype and you just need something to work, that extra development effort can be quite a pain to learn new registers and register names for your architecture. In that case, the abstraction layer that Arduino introduces is a wonderful blessing. Being able to call digital write instead of having to figure out which bits to flip in which register is fantastic. All that being said, if we want to do more advanced things like set up interrupts, then learning how to deal directly with registers is the way to go. We'll talk about that next time we look at leveling up your Arduino code. See you then!